Hello again. Let's look at another example, and let's stay in the safe world of preorders and sets. So remember that we had this forgetful functor which forgot about the order structure and just returned a set, and we managed to find a right adjoint to this, which was the thing that took a set and gave us back a preorder where everything was related, right? So now let's see if we can also find a left adjoint to this thing. So what would this mean? Well, it will mean that maps into forget of x. So that's just a set. So a function from a set, into this thing should be the same thing as something applied to a and a monotone map into x less than, right? So because the function up here, we don't know anything about what this is doing, that means that we should make it as easy as possible to make an order preserving map down here, right? So how do we make it as easy to preserve something as possible? Well, we make sure that it never happens in the first place, right? So if we make this what's called a discrete relation, then we should be good. So we can't quite make sure that nothing is related here, right? Because this still needs to be a preorder, so it needs to be reflexive and transitive. But we could make it so that the only things that are related are things related to themselves, right? Because that would take care of the reflexivity, and transitivity then just means that you can never have two different things related, so we don't have to worry about transitivity. The only way this happens is if they are all equal anyway, right? So let's see if we can do this. So we are saying that discrete of a again, we need the underlying set to be a, otherwise there's no way we can use this function up here. And then we're saying that the order itself should just be equality, right? So this is reflexive, and it is in fact the smallest reflexive relation. And then an order preserving function from here to here, well, that should just be an equality preserving function, and all functions are equality preserving. That's what the Kong combinator says, right? Okay, so let's see if we can do this. So first we have to define a functor. Okay, and we already said what we wanted to do. Here should get given a set A. And we have to return a preorder. Okay, so we said that the carrier should be A. The relation itself should be equality. Here we have to show that equality is reflexive. Well, it certainly is. And here we have to show that equality is transitive. Well, it is that as well. Finally, we have to show that it's propositional. Well, we have this uniqueness of identity proofs principle in Agda, which says exactly that. There's at most one identity proof. So that was easy. Okay, is this functorial? If we're given a function f, can we make a monotone map out of it? Well, on the underlying sets, we can use the f we have. And now we have to show that this is preserving equality. Well, that's exactly what Kong of f says, right? Or we could pattern match on the proof here and then see it re-implement Kong. Okay, does this preserve the identity? Well, it's enough that the underlying function does, and it certainly does. Does it preserve composition? It's enough that the underlying function does, and it certainly does. So we do have a functor. Now let's see that we really have this to and from that we want. So in 2, we need to take a monotone map H and turn it into a set map. Well, but H comes with an underlying thing again, I think, yes, so we can use that. And going the other way is the interesting direction, right? Where we are given just an ordinary function and we have to upgrade it to a monotone map. Okay, so that means we have to give an underlying function, just the one we are given. Otherwise, our round trips are not going to work. And we have to show that it's order preserving. But here, let's see, so we're given an x and a y and a proof. And we have to show that k of x is smaller than k of y. Okay, that seems hard, right? But we know that x is equal to y. So a pattern match on that proof. Then I just have to show that k of x is smaller than k of x. But I know that b is reflexive, right? So start to introduce b. And then I can use the fact that b is reflexive to prove exactly this. Right, so it works because we're working with preorders, so that we really have reflexive relations. Otherwise, it wouldn't work for arbitrary orders. Okay, let's see here. We're given an h. We have to show that the round trip is the identity. Okay, this is an equation of monotone maps. So it's enough that the underlying things are equal, and they are. Here we're given a k. And it's easy to show that this is equal to itself. So that's because we took the k, we used k as the underlying function, and then we just returned the underlying function, which is k again. So that round trip was easy. What about here? We're proving that it's natural, so we get given the f and the g. We have to show that two functions are equal. Okay. And now we have to show that these are equal. I think they are. Yes. So maybe we didn't really need to do that. No, it was fine anyway. Okay, so we have managed to find two different adjunctions to this forgetful functor. One right and one left, which makes this functor rather special. So many functors have no adjoints at all, but this one has both a left and a right one, which makes it really nice to work with. That explains a lot of the nice properties of the category of preorders. And as you can see, doing this in Agda is a bit fiddly, so it's really best to do this on paper first. And then once you figured out what the functor should probably be, then you can try to convince Agda that you have the right thing. It's sometimes helpful because you can just write REFL and Agda will check that this is the right thing and you don't have to work it all out on paper. But the high level thinking is definitely for you and not for Agda to do.